the digital camera. The next part we are going to see is color. So there are three primary colors: red, green, blue. Additive colors, they are called as additive colors. All these additive colors can be mixed to produce cyan, magenta, yellow, and white. On combining red and green, we'll get yellow. On combining blue and red, we'll get magenta. On combining blue and green, we'll get cyan. On combining all these three colors, we'll get white. Subtractive colors are known as cyan, magenta, and yellow. On combining these subtractive colors, we can get back the original additive primary colors. So magenta and cyan produces blue, cyan and yellow produces green, yellow and pink produces red. Combination of all the three produces black. So these are the primary and secondary colors. These primary colors are based on or the nature of human visual system. They are called as tristimulus or trichromatic. So a trichromatic theory test involved reproducing all the colors by mixing three chosen primaries. In 1930, CIE Commission Internationale Éclairage standardized the color values. So, in order to identify the pure red color, they have defined the value as 700 nanometer wavelength. If it is above 700 or below 700, there is a change in red like maroon or pink, so and so. Green, we may see different green colors, right? The pure green is 546.1 nanometer wavelength, and the pure blue color is 435.8 nanometer. A value around 400, 400 plus or 435 plus may see a change in blue, light blue or dark blue. So we can see the diagram here, and just note down the value here. Blue is 435, green is 546, and red is a vast high range 700. So when we try to mix green and blue, more or less it will be in same range. So it may not combine with the red. So in real time, the adding of green and blue is okay, but when combine red with blue or red with green, we have to add more amount of red that will result in a negative value. That is what represented here. While mixing of colors, we need to add more red color that results in negative value, but in negative value representation is not possible in real time. So in order to normalize it, we are going to convert it to the XYZ. So let us see a formula how to convert the RGB value into XYZ formula. So RGB wavelength we know 700, 400 and 500 something. So on converting this to XYZ, we have to apply the matrix 1 by 0.17697 and a 3 cross 3 matrix. On applying this matrix, we may get RGB value into XYZ. This will convert the negative value into a positive value. RGB may contain negative value, but XYZ only contain the positive value. This XYZ can be converted into a chromaticity coordinates x comma y comma z using this formula: x equal to x divided by x plus y plus z, and y equal to y divided by x plus y plus z, and z equal to x divided by z divided by x plus y plus z. This is the chromaticity diagram. So we know the wavelength, right? Blue is 435, green is 546, red is 700. So based on the human visual perception, the chromaticity diagram is represented. So 400, around 460 we see the blue color, around 540 we see green color, and around 700 we see a red color. So on combining red and blue we get purple, and on combining blue and green we may get cyan, and on combining red and green we get yellow. On combination of all these three provides a white color that is represented as E. The next curve is Macadam ellipses. So here we may see a dot with few ellipses. This shows that our human eyes are not that much distinguish the small color differences. So the smaller ellipse says that our human eyes are less sensitive to changes in the colors. So you may observe that there is a change in color on these ellipses. So which where the human cannot distinguish the smaller color differences are represented as ellipses. Next, the color cameras. Every camera have a separate sensor, and each sensor will capture different sensitive values of images. So they are represented as SR, SG, SB. Okay, so in order to make it standardized or normalized, we are performing integration with L lambda, that is an incoming light spectrum, SR lambda and D lambda. We have already seen about the incoming light spectrum in the beginning of the unit geometric primitives. So the incoming light spectrum is multiplied with sensitive sensor specific sensitive value SR lambda and D lambda. Similarly, RGB. These camera specific sensors are converted into the normal RGB colors. As we already know, normal representation of RGB may result in negative. So we are performing again a matrix multiplication and we are converting it into the XYZ value. Next, color filter array. Most modern camera uses a color filter array, typically the Bayer pattern. This is the Bayer pattern. So you can see a 4 cross 4 matrix. In this 4 cross 4 matrix, we can see 1, 2, 3, 4, 5, 6, 7, 8. 8 green pixels and 4 red and 4 green. So out of 16, we are having 8 green and remaining 8 divided into 4 red and 4 blue. So what they are trying to say is it has more green filters which will match the human sensitivity to luminance. Okay, human eyes are more sensitive to the green color only. So this color filter array is represented using this Bayer pattern. The next step is the process of interpolating the missing color values to have a valid RGB values for all the pixels is known as a demosaicing. So in this we have to find the missing values. So here we have a green pixel. So remaining two are R and B. Here we have a red pixel. Remaining two are G and B. So the same matrix is considered here. So the known values are represented in capital letter. The unknown value we are going to find is represented in small letter. This process is known as demosaicing. Next, color balance. So in order to balance all the neutral colors, they will be trying to appear as a white. That is known as color balance. Before saving an image, cameras apply color balancing to adjust the image's white point, making a neutral colors appear white under different lighting. One of the simplest method is scaling each RGB value with a diagonal matrix. We'll focus only on diagonals. If you want to perform more advanced methods, means a full 3 cross 3 matrix will be considered to make the color balanced as a white. The next one is gamma. In the beginning of the digital camera part 1 video, we have seen a pipeline, right? The first step, what we have discussed is optics. Optics means converting a scene to a sensor. How the scene will be converted to a or given to the sensor means the light will be falling on the object or light will be falling on the scene, which will be converted to the photon or electron. Then it will be converted to a voltage, which will be given as the input to ADC. That is what we have seen in the beginning. So the brightness is directly equivalent to the voltage. So in real time, brightness of the screen doesn't increase linearly with the input voltage. This is a non-linear. This non-linear relationship is called gamma. The voltage depends on the voltage only, or brightness will be determined in the image. This voltage is exponentially increased with gamma. Based on this gamma value, the brightness will be increased or decreased. In other color spaces are YUV, YIQ. In addition to RGB and XYZ, we have few more color spaces. They are YUV and YAQ. Y represents luma, UV represents chroma. Y alone represents the brightness information. Apart from image, only the brightness are represented. If you apply a filter of brightness, you may see the differences, right? So that brightness is depends only on the Y, and UV represents the chroma. The remaining color information is represented in UV. Based on the RGB value, we can get the luma as well as the chroma. 0.299 R dash plus 0.587 G dash plus 0.114 B dash represents the luma value. Subtracting of B with the Y dash and R with the Y dash, we can get the chroma components. Then the compression, after converting into YCBCR, this YUV is also known as Y CBCR, Y represents luminance, CBCR represents chrominance. So after getting this, we'll again subsample it. We'll not directly process all the data. We will do subsampling in the ratio of 4 is to 2 is to 0. So all the subsamples are divided into 8 cross 8 blocks. Every 8 cross 8 block is applied with a discrete cosine transform, which is nothing but Cohen-Loeb transform, which is a theoretically proven optical transformation for data compression. So what it will do means it will extract only the optimal or required coefficients to be processed next. After getting the coefficient, we will perform two more steps. One is quantization, another one is entropy. The coefficients obtained from this discrete cosine transform is further reduced in the process of quantization. Then the quantized coefficient is encoded using this entropy coding. Few techniques are Huffman coding and arithmetic coding. This finally results in a very compressed one which contains only the necessary informations. Next one is this. This is up to for image processing. If you are performing video compression, means one more layer called as motion compensation is added. Generally the video, how the video is formed means based on the previous frame, the current frame will be generated. So it will predict the next frame based on the previous frame. So in case of image, we'll perform the compression on 8 cross 8 blocks. In case of video, we'll perform the compression on 16 cross 16 blocks. That's why the size of the video is high when compared with the images. So after performing all the compression, we have to check the compression quality, right? Whether we have done the right compression or we have done large compression or low compression, we have to check the quality, right? So it is done by PSNR. The formula is 20 log based on Imax RMS. Imax represents the maximum compression ratio and RMS is the root mean square between original image and the compressed image. So based on this error rate, we can determine the compression quality. That's all. Thank you.